So, hello, my colleagues, my friends. Let us start today session. Today it is a little bit more short because today we have a business day in Russia, and yesterday it was a holiday. Okay, Manju, please begin your lecture.
Okay, so thank you, Lima. Welcome everyone. So so let me just continue where I left off. So yesterday, just quickly, we introduced the log gas So I introduced the log gas, which was this joint density of particles, e to the minus beta n square h of lambda. And for most part, we are taking the quadratic one. And the main point was this tridiagonal matrix, which is supposed to be useful for that. So I was going over that if you take this tridiagonal matrix with independent entries, normal 0, 2, and bk squares are chi-squared random variables with certain parameters, then the distribution of eigenvalues is exactly the quadratic log gas. So this was what I said, and we were going over some of the uses of it. One of them was that all the eigenvalues are in -2 to 2 with high probability. And second, I was going over the Wigner semicircle law. Let me just continue and finish that one off. So what is it that I did yesterday? So I take this random matrix, which I had written here with Gaussians and chi random variables. And then, but we have a scaling by square root beta n. Therefore, I can, so AK by square root beta n is very small, and BK is approximately like square root beta times n minus k. That's what a chi random variable looks like. So bk square is like beta times n minus k. So bk is like square root of beta into n minus k plus a Gaussian. That's what it looks like. So because of that, I just simplified the random matrix to the following one. So if I take into account the scaling, I get this random matrix where there are it's tridiagonal, zeros on the diagonal, and square root 1 minus 1 over n, square root 1 minus 2 over n, etc. on the off diagonal. Okay, so these are the this is the random matrix, and what I did yesterday was that the spectral measure at E1 converges to the semicircle distribution. That's what I did, mu E1 Tn, and I left it as exercise to do mu E2 Tn, mu E3 Tn, etc. So for any fixed del, you will get some different measures. What I want to do is for the empirical distribution, which is Ln, which is the 1 over n delta lambda k. Okay, so this puts equal mass at all the eigenvalues. This is not spectral measure at, I mean, this is not necessarily okay, so this is spectral measure at some random vector, but that's not the way. We think of this Ln as the average of the spectral measures over an orthonormal basis. We can say it that way. So this is the one that I want to calculate the limit of, and I say that it becomes semicircle. But before that, I was so even with the spectral measures, if I take at some k, which is approximately n times u. So this earlier I did it spectral measure at E1, but if I take it at say some fraction of n, at fraction of n, then it turns out, so we can calculate that. Let me quickly just do that. So this one is easy actually. So what is the spectral measure at a vertex at a coordinate vector ek, where k is n times u, where u is strictly between 0 and 1. So then x to the p, the pth moment of that is just the Tn to the p k comma k entry of that matrix, which is expanded like this, where I1, okay, I did not write, sorry. So let me erase this. So this is not written correctly. So k is fixed now. So what I have is that, so here I1 has to be equal to k. So that's where we start and end. And each ij and ij plus 1, ij and ij plus 1, they differ by 1 or minus 1. Because we have zeros on the diagonal, they have to change by plus or minus 1. So I have to calculate this. Now it's similar to the situation with the other one, except that what we are looking at now is to start, so here we have square root of 1 minus k over n in the k comma k plus first entry. And then we will have square root of 1 minus k plus 1 over n, etc. So approximately all these, so if we fix P and look at T of I1, I2, I2, I3, etc., all those entries are approximately square root of 1 minus k over n. So we can write that this is approximately 1 minus k over n, square root of that to the power P, so which is P over 2, times the number of paths which start at k, and so the number of walks on integers or integer plus from k to k in P steps. Now that is easy to work out. The thing is, unlike before, k is not 1 here. So k I am taking to be approximately n times u. So this is actually 1 minus u raised to the power. So let's say p is an even number, otherwise you get 0. If p is an even number, you get 1 minus u raised to the power q in this. And the number of walks, the restriction completely becomes unimportant because p is small, and so k is quite far away from the boundary of this z plus. Therefore, you just get 2q choose q here. So there is no factor, there is no 1 over q plus 1 factor, unlike what I got last time. That was for the restriction that walks have to stay above 0, starting at 0. But here there is no such restriction, so you just get this. What are these the moments of? This is actually 1 minus u raised to the power q times, let's write it as expectation psi to the power 2q, where psi has the arc-sine distribution. So psi has arc-sine distribution on minus 2 to 2. That means that the density looks like density is 1 over square root of 4 minus x square. So it blows up at the two ends, so it looks like this. So this is what the arc-sine density looks like. And so this is basically, so what we are getting is that, so mu E nu Tn is converging to a scaled arc-sine distribution. Okay, it's converging to, in fact, you can write down what is that scale. It is 1 minus u raised to that power. So it is converging to, in distribution to this random variable, square root of 1 minus u times psi, where psi is this arc-sine random variable. Okay, so that's what happens. So for every different k, the limiting spectral distributions are actually different. Now, what happens to ln? So let me finish that one. We have all the calculations we need. We don't really need to do much. So if we are looking at ln, it is the average of all these things. Of all these spectral measures. So basically, well, let's just write the integral, for example, x to the p. I don't need to say in terms of moments. I can just, well, anyway, let me write it like this. X to the p dln of x will be, you will get the moments of all these things. So you will just get 1 over n, k equals 1 up to n. And what did I get for the pth moment of that? So let's take p equal to 2q. All the odd moments will be 0 always in these cases. So you will just get 2p choose p times 1 minus k over n to the power q. Oh, sorry, this is 2q choose q. So what I have here is 2q choose q, 1 minus k over n to the power q, which is approximately like the integral. So it is 2q choose q is expectation psi to the power 2q, right? And what is this? This is the integral of 0 to 1, 1 minus u to the power q du. So basically it is, so the thing is, so these are the moments. So another way to write it is, so you can write this as expectation of psi square root v to the power 2q, where psi as before, psi is arc sign like before, and v is uniform on 0 to 1. And these two are independent. If they are independent, then you get exactly the expression that is here for the moment of this psi root v to the power 2q. So in other words, so the ln converges to, so the distribution that we want, what is the distribution of psi root v? That's the question. Psi square root v. So you can think of it as a superposition of scaled arc signs, but with the weight given by this square root v 1. And anyway, this is very easy to work out, but actually I didn't have to do that. Here the integral is explicit, so I could have simply written, sorry. Yeah, that one is actually semicircle, but that is actually apparent from here. So if you do this integral, you get q plus 1. So psi root v is actually has the same distribution as semicircle distribution on minus 2, 2. This was the semicircle distribution with density square root of 4 minus x square. So in other words, ln converges to sigma. Okay, so this completes the proof of Wigner's semicircle law from the tridiagonal matrix. So for those who have seen other random matrix models, I mean, like for example, from GUE or Wigner matrix, the combinatorics here is way simpler. That's the one point. Okay. Okay, so that was the other use that I wanted to show before. So there's one more, but I will come to that. What I want to explain next is then I want to go on to explain. So there's one more which I will come to. So that let me explain how this tridiagonal matrix comes about. Okay, so the tridiagonal matrix is I mean, I did not explain why this is true, etc. So let me just give a brief explanation of some of the things here. Okay, but if there are any questions before that, I'll be happy to take always.
Sorry, you didn't explain that is true. What? It was just a definition.
I did not explain. I mean, so I just stated this fact that this matrix, its eigenvalues have this density.
Okay, you didn't explain this. Okay.
I did not explain this part, how this comes, etc. So I just want to give a brief explanation of that. There are two ways. So this is related to the question you asked yesterday. I will come to that. So let me now explain that. So what is it that why these tridiagonal matrices work? Okay, so what we have to do is so one way, there are two ways. Well, the first way it was discovered by Trotter. That I will come to later. That's kind of interesting. So I will go over that. But this first one is kind of a bit boring. It's good that it works, but it looks boring. And so basically, what is it that we have? We have A and Tn is our matrix. AIs and BIs are some random variables. So we have explicit density given for this, whatever be the density. What we want to find is the density of eigenvalues. Obviously, you have to introduce some auxiliary variables and make a change of variables. But what are the auxiliary variables that you need to introduce? That is the question. So these things are a bit cleaner here than with the GUE matrix, for example, or in some ways cleaner. So here we have a total of 2n minus 1 real parameters, right? So there are n diagonal entries and n minus 1 off diagonal entries, b1 to bn minus 1. So there are 2n minus 1 parameters. On this side, I want eigenvalues and something else. So eigenvalues will give me n parameters, but also the correct auxiliary variables is to just take, so there are n lambda k's, and if you look at the spectral measure at E1, that will give you another n minus 1 parameter. Since that's a probability vector, it is actually n minus 1 parameters. So you have a total of 2n minus 1 parameters again. So this looks reasonable. And in fact, this is a bijection between, if you look at A in Rn and B in strictly positive, BIs are strictly positive, then this maps this side to, so this is a bijection actually. that you on this side, lambdas can be anything Rn. So to just make it very identifiable, I have made Rn plus means I order them, because eigenvalues don't come naturally with any order. So I order them lambda 1. So that's what I mean by putting this arrow mark here. Rn upper arrow means they are ordered. So lambda will be there. And sorry, this is and strictly, and these are distinct. Okay, that is also part of what I'm saying. And P is in the, this is the open simplex. So PIs are strictly positive numbers which add up to 1. So this is actually a bijection between these are called Jacobi matrices on the left, and these are the spectral measures at E1 for them. So these are the measures supported on n distinct points in Rn. Okay, so that's a bijection actually. And one way is clear. So one way is from the matrix you go to this one by taking the spectral measure. How you come back? Okay, I don't want to get into that one now. Maybe it will be clear from some discussion later. But let me just leave the assertion that it is a bijection. And what you need to know is the Jacobian determinant for this. Then you can hope to transfer density on A. If you have a density on A and B, then you can hope to transfer it. And if you are lucky, it will be explicit on the other side. You can close it. So that is the main point. So the main calculation is this one. So what I have written here. So this thing is the main calculation. That the determinant, the Jacobian determinant of this inverse map is actually B1, B2, Bn minus 1 over 2 to the n minus 1, P1, P2, Pn. Okay, so it is kind of, it is written in a mixed way with using variables on both sides. So it is G inverse at lambda comma P. That's what I wanted to write, but it's not, you cannot write it in a very closed form expression in lambda and P. So I have written it with variables on the other side where BIs are coming from this correspondence. Okay, so that is what it means. So the Jacobian determinant has this explicit form. So this is actually the main calculation, and which I will not do. It is written in the second, the notes that I have referred to, it is given in detail. So Forrester's book, Peter Forrester's book, Log Gases and Random Matrices, has all this stuff in full detail actually. So my notes, pretty much I took it from there, this part. So, and there is this mysterious identity which I cannot explain. I don't really know what it means, but there is this strange identity which relates variables here to these variables. I mean, there is a particular, of course, everything is related to everything on the other side because of the bijection, but this particular form of this particular combination has an explicit formula in terms of the variables on the other side. Okay, so this product bk to the power 2 times n minus k is the same as product pk times the van der Waals square of the lambdas. Yeah, so this I don't know where, I mean, why it is, I can prove it, but I cannot explain what it means. I don't know what it means. Yeah, so you have to use that. So for example, when you use that, you see that here, this product pk or BIs, you can write the van der Waals squares coming out here. Okay, so the b's, I have to remove the b's. Okay, so what we do is the density that we put on this is basically, what do we put? We put e to the minus 1 by 4 summation ak square. That is from the normal CO2 random variables. And then there is the bk's that also come about. They will be like e to the minus 1/2 summation bk square, because they are bk squares are chi-square random variables, and bk to the power beta times n minus k minus 1. Something like this is the density on the left side. Now, one part of it is okay. The exponent, in the exponent, you have summation ak square plus 2 times summation bk square, which is actually trace of the square of the matrix, which is also summation lambda k square. That is how we get, on the other side, we get e to the minus 1/4 summation lambda k square. This comes, this factor comes. The problem is what happens to this thing is, and that's where this identity plays a big role. You have to take this identity as well as put in the Jacobian determinant, and then you work out, you get the van der Waals raised to the power beta. Okay, so that's the, so you see bk to the power 2 times n minus k gives van der Waals square. So to the power beta times n minus k will give a van der Waals to the power beta, basically. So one has to work out the details. So I will not do that here, but this is the basic proof. This is the proof. And so, yeah, there is a little bit of calculation involved in this. So how do you do the change of variables? But it is, okay, it's not overly complicated. Okay, so that is one, that is the way, but this is not the way it was found. I mean, so why somebody would think of actually finding this change of variables? Maybe there are natural reasons to think of it, but at least that's not the way it happened. The way it happened was different, and that has a nice nice idea. So maybe I indicate that. So what did Trotter do?
Manju, can I ask?
Yes.
It's interesting that there are no A's in this identity. Can you comment on this?
So in the there are
no A's in this identity.
Yes, yeah. Yes. So
of course, it might happen, but can you comment this?
No, I cannot actually. I don't know. I mean, yeah. So can we see that A's should not be there in this? No, sorry. Sorry, I don't know. I mean, I cannot think of any good reason to give why A should not be there.
Okay.
You want an explanation? For example, what would be good is if you take the right hand side and say that it doesn't depend on A's. That's what you're asking. I don't see that. Yeah. No, sorry. Any other questions? Okay. If not, let me explain how this first came about. So this way, this was basically done by Edelman and Dumitriu. So let's. In 2000, but before that, in 1984, Trotter had already got a tridiagonal model for GUE or GOE. So there was already these random matrices, GUE and GOE matrices, and from there he came to this tridiagonal by a series of similarity transformations, which is very nice. So maybe I explain this in the assumption that people, if everyone had, I wouldn't know, that's the problem. If everyone has seen it, it may get boring, but otherwise it is very beautiful. So maybe I will show this. Okay, so what is GUE or GOE? So I defined GUE last time. So let me just define GOE in a different way today. So GOEN is, what is this? It is basically, so you look at all the set of n cross n real symmetric matrices. So this is a Hilbert space with inner product AB, which is trace of AB. Okay, so that's the inner product. That's an inner product on this. It's just the same as looking at them as n squared by 1 vectors. Now, what is the GOE measure? GOE measure is the standard Gaussian measure on this space. Okay, what is standard Gaussian measure? Whenever you have a Hilbert space, this is a finite dimensional Hilbert space, you have Lebesgue measure, and the Gaussian measure is just e to the minus AA by 2, and then we take the dA over 2 pi to the dimension by 2, which the dimension in this case will be n into n plus 1 by 2. So something like this will be there. So the dimension of this space is, I think, n into n plus 1 by 2. So then you will get that. So this is basically the GUE, this measure, matrix chosen from this measure is what is called GOE random matrix. So it is e to the minus 1/2 trace of A square. That is the, okay, with the constants. So this is the GOE matrix. So GOE matrix is exactly the same. Yesterday I defined it differently, but it's exactly the same with n cross n complex Hermitian matrices. It is the standard Gaussian measure on that space. And the main, most important property of standard Gaussian measure on any space is the orthogonal invariance. Okay, so the orthogonal invariance tells you that under orthogonal transformations of the Hilbert space, the measure stays invariant. So this Zakha was using a lot this idea yesterday also. So because to convert uniform measure on sphere to, I mean, some integrals with respect to Gaussian. So the same idea. So orthogonal invariance of Gaussian means, so there are particularly the following unitary transformations on. So if U is a, or let me, yeah, if U is an orthogonal matrix, n cross n, okay, despite writing U, that is orthogonal, not unitary. So U is an orthogonal matrix, then you consider this map from, I didn't give a name for this, so this n cross n real symmetric matrices, let's call it Hn. So then you can define a map from Hn to Hn, which is sending a matrix A to U, A, U star. So this is an orthogonal transformation actually. So this mapping is orthogonal on Hn. So because of that, so if I say a GOEN matrix, so let me call it AN. So what that means, sorry, I use the same A. So this means AN, the GOE matrix has the same distribution as UAN. Okay, so this is transpose UAN, U transpose for all U in the orthogonal group. So this is the orthogonal invariance because of which it is called Gaussian orthogonal ensemble. It is Gaussian and it is orthogonal invariance. So it's called a Gaussian orthogonal ensemble. And this is the main property that one needs to use. So what Trotter did was, so starting with this, so let's write this AN. What he showed was, so let's write AN like this. So at first, let me write it like this. So you write the 1-1 entry, which is, let me call it, well, just call it A. Okay, let's call it A. And then there is the entire vector below that. Let's call it V. So what we have here by symmetry is V transpose. And let's say we write this B here. So this is an n cross n matrix. So B is an n-1 cross n-1 matrix. So suppose you write A like this. Now, things that are to be noted are A, V, B. These three are independent. Okay, they are independent of each other. Okay, so A, V, because of the, well, okay, so one has to see that from here, the trace of A square will come out as sum of squares of the entries. So obviously there is a factorization. So A, V, and B are independent of each other. Now, also B is, so what are the distributions? A is just a normal, what is it? E to the minus A1 square. I guess it's normal 0, 1 maybe. And what is V? V is a standard Gaussian vector in, oh no, it is actually, right. So it is actually, it's not standard Gaussian vector. It is because V e to the minus trace A square will have, A square will come once, the 1-1 entry, diagonal entries will come once, off diagonal entries will come twice. So the variance of that will be 1/2. It's a Gaussian vector in n-1 dimensions with the variance 1/2. Okay. And B is just a GOE matrix of size n-1. Okay. So these are, and these three are. It's 9 o'clock. Okay. So then what the first thing is, so you can find P in the n-1 by n-1 orthogonal group such that it brings this vector v to the standard form r 0, 0. Okay, it brings it to this form. Naturally, that r has to be the norm of this v, no doubt about that. But there are many orthogonal matrices which can bring v to this standard form. There is an explicit one called, which is a reflection matrix. What you can do is there is this v, this vector v, and the vector to which you want to go. Okay, so you can imagine the tip of these vectors. I mean, okay. So the midpoint of this, you join these two vectors by a straight line and take the hyperplane bisecting that. Reflection in that hyperplane is one explicit one which you can write down. It's very explicit transformation. It's called a householder reflection. Okay, so that is one explicit example one can use, but one can use anything. But the condition here is the following: this P should be chosen only based on V alone. You are not supposed to look at A and B when you choose this matrix P. That's the only choice. So other than that, you can make your choice. You look at the vector V and choose P. Okay, so that's what you have to do. So then you can conjugate this A by this n by n orthogonal matrix, which is 1 P 0 0 an 1 0 0 P transpose. What does that do? So because of the 1 there, the first entry will remain just as it is. So this will be A. Okay, let me write down all the entries. So this will be, this vector in block form will be V. This will be V transpose P transpose. And what we will have here is P, B, P transpose. Okay, so by choice of this P, this is actually A here. Then we have R and zeros here. By symmetry, it is the same, R and all these zeros here. And this PBTP transpose, let me call it C. So now again, A, R, C are independent. Okay, that's one claim. Why? Because well, the fact is this, yeah, it's clear. P was chosen based on V alone. That's the point. And why is but C also has this PBP transpose. Why does it not matter? Because irrespective, if you fix that P, since P is a GOE matrix, by what I said about the unitary invariance here earlier, PBP transpose is just a GOE matrix. So conditional on P, it's a GOE matrix. So unconditionally also it's a GOE and independent of P. So C is independent of the other things. So it is a GOE n-1 matrix. A has not changed at all. It is the same normal 0, 1 that used to be there. But what is R? R is the norm of a Gaussian vector in n-1 dimensions. So its square is a chi-square distribution with n-1. Okay, I have messed up a little bit, I think. So something is wrong. Yeah, so it would have been better if I had made this normal 0, 2, I guess. So that was how I wrote it in the beginning. So maybe I just do that small change here. It doesn't matter. It's an overall scaling. So, but that is, that will prevent me from getting confused later. Normal 0, 2. In that case, I don't need this half here. Okay, so there's an overall scaling applied here. So then this will be normal with mean 0 and variance 2. And this will be a chi-random variable because it's n-1, sum of squares of n-1 Gaussians. It is the square root of a chi-square. So we'll just write it as chi n-1. So now you can iterate this. So you have reduced this to this form. Now you take this C, which is an n-1 by n-1 GOE matrix. You apply this to its first row and first column. You do that and continue. So what you end up with is this exactly, A1, A2, etc., AN, and then you will have this I'll change from B to R to B, B1, B2, etc., Bn minus 1, and the same things on the other side. Everything remains the same. So A case will be normal 0, 2 always. But bk square, the size of the Gaussian vector keeps decreasing. At first it was n minus 1, next it will be n minus 2 and so on. So bk square will be a chi-square with n minus k degrees of freedom. Okay, and all these are independent. The independence is carried through the whole procedure. So this is how he arrived at this tridiagonal matrix. So because all this is similarity transformations, the eigenvalues of this are exactly the same as the eigenvalues of the matrix you started with. And so this, if you look at this random matrix, its eigenvalue distribution is the same as what you started with. And for GOE, it was known that that is the log gas. Anyway, what Trotter wanted to do was to prove Wigner's semicircle law from here, which he did exactly the way I showed it. Okay, so that was Trotter's idea. I think it's a very beautiful one. So this tridiagonalization, apparently this is used routinely in numerical linear algebra for calculating eigenvalues of a symmetric matrix. It is first reduced to tridiagonal form, and then apparently that is how these algorithms, many algorithms work. Okay, so I wanted to, so of course, the thing that Edelman Dimitriou did, one can interpret as, at this point, they realized that you can change bk's to the parameters to beta times n minus k and get this other Van der Waals to the power beta also. Okay, so that's how the tridiagonal matrices came about. Okay. So that ends this.
Sorry, I didn't get how you went from beta 2 to arbitrary beta, because when beta 2, you can use the explicit form of this log gas using Gaussian matrices. But
so you cannot. So that's right. So I did not actually show how that comes. So if you want to do that, the one method I suggested is you just forget all this tridiagonalization. You just compute this Jacobian determinant, then you make this, you do these calculations, then you get the eigenvalue density. So this one is how Trotter had come to. Somehow I feel that if one doesn't, okay, my just remark is that if someone had not done it from GUE or GOE matrix, I wonder if anyone would have thought of just making a tridiagonal matrix like this. So the fact that this was there, or it was in fact rediscovered probably a couple of times, so that actually then it becomes more natural to wonder whether we can generalize to other distributions at the level of tridiagonal matrices. But yes, this itself does not give the proof. Any other questions or comments? Okay, so that is for the tridiagonal matrix for the for this beta log gas with the quadratic potential. So there are other standard random matrices. So let me indicate. So 3 questions. So one is there are 2 other families of random matrices which often come. So there is this Legge ensemble and the Jacobi ensemble. So let me say what is the Legge ensemble. Legge ensemble is the beta log gas, which the density looks like this. It is e to the minus summation lambda k, or let me just, So let me write it like this. So the density is product lambda I minus lambda j to the power beta. That is what we want, the interaction, times the measure with the product measure. Earlier was Gaussian. Here it is going to be a gamma measure. Okay, but this is on R plus to the n. Okay, so this is, so in other words, if you take the original form, so you want all the particles to live in 0 infinity. So you have to set the potential to infinity on the left side. So if you take the original form in which I wrote the beta log gas like this, the energy you want to be infinite when lambda k is negative. So you set the potential infinity on the negative axis, and it is, and what is it on the positive axis? It will be, sorry. On the positive axis, it will be my x plus log x, x plus x minus a minus 1 log x or something like that. Anyway, so this is the density. So this is also this occurs in the when beta equal to 2 or 1, it occurs in the as the eigenvalue distribution of covariance matrices of standard Gaussian vectors, okay, or complex Gaussian vectors for beta equals to usual Gaussian vectors for beta equals 1. So this is a standard ensemble which occurs in random matrix, and there is another one called the Jacobi, which is the one with the density where you have the van der Waals with the product measure, which is just any beta measure. So you take lambda I to the a minus 1, 1 minus lambda I to the b minus 1. This is on 0, 1 to the n. So this is the density where here a and b are parameters positive. Here a is a parameter which is positive. Okay. So these are also standard ensembles which occur, and this is the this comes from yeah, this is a matrix analog of what is it? It's called either T distribution or F distribution, one of the two. Okay, so it's like a yeah. Anyway, so I don't want to explain that. So the thing is, so these also have explicit sparse matrix representations, which I have indicated here. So for example, what is then, so for beta equals 1 and 2, I said this comes from covariance matrices, but for general beta, there is no full matrix model, but there is a random matrix model which is sparse, which gives you that distribution of eigenvalues. Okay, so what is this random matrix? You take this Ln, which is a 2n by 2n matrix. Okay, so it's 2n by 2n, so I'll have to explain a bit. So what is on the, so there are, it's tridiagonal, so zeros on the diagonal, and everywhere these are zeros, and up, down here, and up there. And on the off diagonal, you have a1, b1, a2, b2 up to bn minus 1 an. There are n ai's and n minus 1 bi's. So what are these? These are independent, first of all. These are independent entries. That's what makes this nice. Independent entries. AK squares have chi-square distribution, which is given by beta times n minus k plus 2a. Bk square has chi-square distribution with beta times n minus k. Okay. If you take that, this is a random matrix, but it will have 2n eigenvalues. Okay. So what its eigenvalues, but because there are zeros on the diagonal, it turns out it's easy to see. For every eigenvalue, its negative is also an eigenvalue. So it has n eigenvalues, which I can write plus minus square root lambda 1, plus minus square root lambda 2, and so on. So it has these n eigenvalues, 2n eigenvalues, which are plus minus square root lambda 1. Then those lambda i's will have the density that we want. This is n. This here I have n particles. Okay, so there are 2n eigenvalues, but the squares of those, that is the lambda i's, that has this density. So this is again, you can prove it from the change of variable formula that I did before. So I'll make a remark about these. So for the Jacobi ensemble also, there is a matrix model like this, where you have some beta random variables, and I have not written what the parameters of those betas are. They have to be chosen appropriately depending on the parameter, that beta that we want, and A and B. Those PKs and QKs depend on beta A and B. So in some way, I have not written that, but then again, you have a 2n by 2n matrix. Again, the eigenvalues are going to be plus minus square root lambda n, plus minus square root lambda n, where lambda s will have this Jacobi ensemble density. Okay, so this is called this is the Laguerre, this is the Jacobi. So I must remark that these are actually the forms that I have given are not what you will find in the literature usually. This is actually simpler. I mean, there's no great this, but it's actually a useful remark that if somebody is working in random matrix theory, I have seen at least 2-3 occasions when there is a trick which is very useful. So if anyone has seen random matrix, these Wishart ensembles before, then you would have seen that these eigenvalues when beta is 1 or 2 are eigenvalues of a matrix of the form XX transpose, where X is a possibly rectangular matrix with IID Gaussian entries. The usual way of writing the sparse matrix is also as something like this, as L transpose, where L is a bidiagonal matrix. It has some entries here on the diagonal and below the diagonal. So usually that is the way this is written in most places in the literature, what I have seen. But it can be brought to this form by enlarging the matrix. This is a trick which is actually useful because XX transpose, if you see the matrix XX transpose, its eigenvalues, if they are lambda 1 up to lambda n, positive numbers, then you can consider this matrix 0, x, x transpose, and 0. This is a 2n by 2n matrix. Its eigenvalues are plus minus square root lambda 1 and plus minus square root lambda n. Okay, so equally one might study, if you are objective is to study this, you might as well study this. There is no difference. But this matrix is way simpler. Actually, there are many papers in random matrix where substantial simplification can be done in calculations of this with Wishards if one uses this trick, which is called linearization. So usually the
Manju, may I ask, this second tridiagonal matrix, why the eigenvalues lie in the interval 0, 1?
Okay. I will come to that. I will come to that.
Oh, okay.
Yeah, I'll tell you. So actually, I have not explained what that is actually. So yeah, I will explain that. Yeah. So
okay,
this I have not actually explained the notation. So anyway, so this is a trick, so which makes this actually a nicer one, and analogy with the other tridiagonal matrix is also much better brought out. You just have zeros, and we saw at least in the use that we put to, AIs were useless, so their zeros is okay, and BIs are chi-squares, except that here the odd and even ones are slightly different. That's all. So a lot of calculations can go analogously to that. Now let me come to the Jacobi ensemble. This one, whatever is available in the literature, what I have seen, is way more complicated looking than this. So this is actually, the simplification is useful for the same reasons. So that, so the problem with this, what is the problem with XX transpose as compared to this? Here the entries are linear in the independent variables. Here entries are not independent. They are quadratic in the independent variables. That makes a big difference in some of the calculations. Okay. So anyway, so the Jacobi one is written in a much more complicated way. This was actually not done by Edelman and Dimitriou. This was done, they left it open. Later there's a paper of Edelman and Sutton where they did something which is very complicated, but that is, I don't want that. So this is more or less, I mean, this is not what is written in this paper, but it is equivalent to that in exactly the way I'm trying to say that these two are equivalent. There's a bit more involved. Now, what are these actually? So to address Dima's question, what are these? What is this bar? Okay, so gamma k's are, I just wrote gamma k bar, I mean 1 minus gamma k. Okay, and gamma
okay.
yeah, gamma 0 is 0. So gamma 0 bar is 1. So you see the row sums are 1. They are positive entries, row sums are 1. So you see the eigenvalues are in minus 1 to 1. Because all the row sums are 1, the eigenvalues are in minus 1 to 1. Is that okay? Does that answer?
Yeah, thanks.
So this form I started from the Kilip-Nenchu form which looks complicated, but it's nice, and then you can massage it to this form. I was pretty convinced that there would be a simpler form like this, so I was able to just reduce it to this form. Anyway, so this is fine. But what about general V? That would be an interesting point. So what can we do for general V? So general V means we are looking something like, let's stay with the quadratic type. Sorry, not quadratic. We have e to the minus summation V of lambda k product lambda I minus lambda j to the power beta. Okay, I less than j. Can we find a tridiagonal matrix for which this is the eigenvalue density? Okay, so what Tn? So if I want to pick a matrix A1, B1, A2, B2, so what distribution to put here so that you get this? See, since we have the Jacobian of the transformation, in principle, one can always do it, right? So you want a target density of lambda, which is, you want a target density of lambda, okay? So let's also make P, just like it was in the quadratic case, you can put a distribution on P, which is the Dirichlet distribution. If you know what that is, it's a natural distribution on the simplex. Okay, it's a whole parametric family of distributions, a particular P. So let's take lambda and P independent, but now lambda coming from the general log gas with potential V and P just as before, make them independent. Now you transform it to, by this one-to-one transformation, G inverse, you will get some random matrix here, right? So in principle, it's always possible to do this because you choose your lambda according to this density and you make, as I said, you make P according to the correct one is the Dirichlet distribution with parameters half beta so many times and then make them independent, suppose. Then you apply, you take that as the spectral measure and apply the inverse G inverse and you will get a random matrix. What distribution does it have? Is it any good? The great miracle that happens in the quadratic case is you get some independent random variables here. That is what helps in the analysis. If you take a general V, you can write down a matrix. So it turns out that you can take the matrix with this. So e to the minus trace of V of t. You see, that is what will give summation V of lambda k. Okay, but what else do we have to put? Times product bk to the power of, exactly like before, beta times n minus k minus 1. You see, these are weights that come in the chi distributions. But now, if you put this distribution, then this corresponds to this. Oops. Okay, so here there is a minus e to the, so if you take this e to the minus trace V of t times product bk to the beta times n minus k minus 1, I'm saying that the eigenvalue density is this. So for this, you have to again go through the Jacobian determinant and work it out. It is easy. So this was done in our paper with Balint Virag and Brian Ryder. So this is a starting point. So what is it good for though? The problem is we don't understand the entries too well. So take the, for example, the case Vx equal to x power 4. Now, trace of t squared, when it's quadratic, trace of t squared is sum of square of eigenvalue. Sorry, in terms of the entries is what I want, not eigenvalues. In terms of eigenvalues, it is simple. It is summation V lambda k. What is it in terms of entries? When it is t square, you have the sum of squares of all the entries, which again factors. But when it is x to the 4, you will get, if you try to compute trace of t to the power 4, you will get things like a1 to the 4 for sure. b1 square or b1 to the 4, all such things come. But you will also get terms like b1 square, b2 square, or a1 square, b1 square, a1, a2, b1 square, etc. So all such terms come which spoil the independence here. But if you are working with x power 4, you will see that only consecutive ones will come. AK will come with either bk or bk minus 1 and so on. So in that sense, there is a Markov structure here. So if you condition on AK and bk, what is above and below in the matrix. So if I condition on some AK and bk, what is on this side and what is on this side become independent. In that sense, there is a Markov structure in this matrix. So we were able to finally use that. It's way more complicated, to be honest. But to analyze at least this kind of polynomial potentials, which we had to assume extra convexity conditions and so on. But we were able to analyze that matrix using this Markov structure. Okay, so that is the why, I mean, that is the general situation. It's not so neat. So why do we care? That is because of this universality question. So yesterday so let me just quickly remark what is the universality question. So we have this quadratic log gas e to the minus summation V of lambda k, or maybe in the way I was doing, I put a e to the minus this product mod lambda I minus lambda j to the power beta. So for the things that I did yesterday, the answers did not depend on beta. The semicircle was the same. The range -2 to 2 was the same. So there was But that is not what I call universality. I mean, okay, universality is a sort of overused, maybe abused word, but what I mean by universality is universality of fluctuations. Like law of large numbers, I don't say universality, but central limit theorem is universality. So the things that we got last time, like Wigner's semicircle law, convergence to a deterministic thing is like a law of large numbers. So that's not what I call universality. Universality is universality of fluctuation. So for example, the maximum eigenvalue. So if you look at, so in this, the particles, so there are particles. So let's say you go from -2 to 2 here. So you can look at the edge, or you can look in the bulk somewhere. So what is expected? So the bulk picture means you have to scale it up to see what is happening there. You scale up so that particles are at unit distance. Or at the edge, you can do the same. You can ask how far is the largest eigenvalue from 2? What's the spacing from the largest to the next largest, etc. So those kind of questions are expected to have highly universal behavior. So what is expected is universality in V. Okay, I mean with some conditions. So with some conditions, but there are V's that you can put where you get exceptions. But there are generic V will have the same behavior like in the quadratic case, for example. But no universality in beta. Okay, so let me be clear about that. The beta makes a big difference. Beta is completely going to change the behavior. But for each beta, the V should not change the behavior much. This is the general belief. Physicists assume this more or less. And these have been proved now to a large extent by different methods. These things have been proved. So this is the general question, which is why this question was relevant, whether for general V we can get this. So there are completely different methods to approach this universality question. Many of the universality questions were open till about 10, 12 years, 10, 11 years ago, and many of them got solved. So there are many different ways. So one of them is all this group that started with Erdős, Line, and Yao. So maybe I won't write all the names here. So Erdős, Line, and Yao, they started this for the Wigner matrices, not for this type of thing, for Wigner matrices. Actually, sorry. So for this type of thing, I should say first there was the Riemann Hilbert methods. So where Deift, Johansson, and many others. So these things were there in the early 2000s. These methods solved this type of universality problem in the edge and bulk, but for specific values of beta equal to 2 or 1, etc. So using determinant structure. Later, people have approached this. One approach is this tridiagonal matrix, and there are other approaches. There is a direct use of density and mass transportation techniques. So this is done by many people, Alice Guionet and Figali. So there is a paper by Figali, Baker, and Guionet, and also Maria Shrebina. So they do it with these methods, and also the tridiagonal method is there. For universality is done only in the edge for this so far. Okay, so there are different approaches, and of course, I didn't say the other big one. So this whole thing with Erdős, Schlein, yeah, that was the first paper, but they have this whole method of heat flow. Pretty much it solves all problems in random matrices, let's say. So they can do a lot of things. It's I don't understand this method, but it's a very powerful method with which they have solved lots and lots of problems of random matrices. So there are other ways. Okay, anyway, so these are some of the things that have been done in recent times. So this universality in V is one of the big features. So universality questions are very common in probability. In random matrix, there has been progress. If you take other models, statistical mechanics models, I think largely it is open. Random matrix is one place where considerable progress has been made in this thing. Okay, so that was just telling some of the problems here. So what I did so far was to tell you how the tridiagonal matrix gives you the eigenvalue density. Okay, that was what I did today, and some of its extensions. So I will now go on to some other thing. So, but are there any questions or comments?
Yeah, maybe a little question about this. You just briefly mentioned that beta equals 1 is also possible to deal with the Riemann-Hilbert methods.
Yes, they do that
really?
actually. So yeah. So they, in fact, beta equals 4 to 4 also, I think. So they do. It's actually more complicated, but there is a Pfaffian kernel, because here you have a determinant process. Here you have a Pfaffian kernel that has to be analyzed. I have never read a complete proof of anything for beta equals 1, let me be honest. But I think Diffe's, okay, let me see if Diffe's.
No, I'm pretty sure it's not true, because you need orthogonal polynomials for Riemann-Hilbert, and it's not the case in when beta is 1 or 4. You have skew orthogonal polynomials then.
Yeah, so but but I think beta equals 1 is no. This is, I'm almost sure that there are these papers of. Okay, I mean, you would know better, but I think Dife, GF, and so on, don't they have these papers for beta equals 1?
Oh, I'm not sure. Okay, yeah, that'd be interesting to check, because I don't know.
Okay, sorry. I mean, I'm sorry if I'm completely stating something wrong, but I will check this.
Okay, yeah, thank you.
I'm not sure that it is there, but it's not something I have ever read or understood, so I'm not sure. Beta equals 2 is there, has a good exposition.
Yeah, there's no question.
Yeah. So.
Yeah, thank you. Thank you.
Any other questions or comments? Okay. So what I want to do, I mean, so just to say a little bit about tomorrow and so on. So my plan is to explain how we get the n to the minus 2/3 behavior at the edge. Okay, so let me, since we are here, so let me explain the heuristic there. So it is a well-known heuristic. So what we know is that the eigenvalues sort of follow this semicircle distribution approximately. So there are n eigenvalues which are sort of distributed. Maybe one of them or a few of them are above also, it doesn't matter. So but just we have these. So what are going to be the gaps between eigenvalues? So since n of them are packed in an interval of length, constant length, this would be like 1 over n. However, that is not quite true at the edge. At the edge, the behavior is different. And what is the behavior there? Okay, so the behavior there is that the spacings are of the order of n to the minus 2/3. So it's slightly larger than 1 by n. So they are somewhat more loosely packed. They stay away from each other. And so the distance is n to the minus 2/3. So this is one thing that I would like to show, how we get it from the tridiagonal approach, and how one can do it from the tridiagonal approach. That I will do probably next lecture maybe. But why n to the minus 2/3? Where does it come from? So that comes from, if you take the semicircle a bit too seriously. Okay, so if you take it what does the convergence to semicircle mean really? It means that if I fix an interval AB, oops, sorry. Okay. So what it means is that if I fix an interval AB, the proportion of eigenvalues here will converge to the semicircle measure of this interval. Okay. But suppose we take it too seriously and apply it to vanishingly small intervals also. So then one expects that if you match the eigenvalues with the quantiles of the distribution. Okay, so suppose you expect that the halfway eigenvalue will be close to the median of the distribution, which is 0, and 1/4 way, the quantiles of the eigenvalue distribution should match with the quantiles of the semicircle. This is just an expectation. If so, the largest eigenvalue will be approximately where the probability is 1 minus 1 by n. In other words, in the semicircle, this probability should be approximately 1 by n. Okay, so that's just a heuristic to say where the largest eigenvalue would be expected to be, where the probability to have any eigenvalues, the expected number of eigenvalues to the right of this. The question is, what is this point? Let's say xn is this point, 2 is here, or yeah. So what is this xn? So that the expected number of eigenvalues to the right of it is 1. 1 is 1. So that would be roughly where you expect the maximum. And but since this behaves like the square roots, this is square root 4 minus x square, so which behaves like a square root. So what you expect is that 0 to 2 minus xn of this density, which we can simply write as square root t dt, should be approximately 1 by n. That's what you would expect. So in other words, but this is just 2 minus xn to the power of 3 halves. So 2 minus xn is, this is n to the minus 1. So you expect that 2 minus xn is approximately like, it should be like n to the minus 2/3. So that is the origin of this, the heuristic for why it should be n to the minus 2/3. Of course, this is no proof. And we'll see a proof using the tridiagonal approach. Maybe I don't know whether all the calculations can be shown. It's reasonably simple, but I will show some aspects of it maybe. Okay. There are many other approaches also to do this for different models. For this log gas, for quadratic log gas with general beta, this is a clean approach that exists. Okay, so that is what I will do next lecture. And the final lecture, I have not fully decided. One option is I will do this, I advertise this last passage percolation, a small result in last passage percolation about a law of iterated logarithm that we did with Milind Hegde, Shishendu Ganguly, and Riddhi Pratim Basu. Maybe I will do that, or if something else occurs, I may change my plans. Okay, so for now, in the remaining, okay, do I have any time? So, Tima, okay, where is the watch? So, I have another 10 minutes, is it right? Hello? Hello?
So, sorry, I forgot to switch. Yeah, you have 13 minutes, 13 minutes.
Okay. Okay, so let me just, so in the remaining time, maybe this will spill over a little bit into the next lecture, which is okay. So I want to just say, what is this whole tridiagonal matrix business? What is it conceptually? Okay, so I just wanted to say a little bit about this connection between Jacobi matrices and orthogonal polynomials. So here there is no randomness. This is all about just deterministically. So tridiagonal, so if you look at a tridiagonal matrix, okay, so let's look at it. Let's take a so let's take this. So Tn is the, okay, let's write first T may be an infinite one also. Tn is the top n by n part of it. So how do I want to write it? No, let me just write Tn since I have matrices. Let me write Tn. It goes up to an and bn minus 1, bn minus 1. So let us say the characteristic polynomial is this determinant of Zi minus Tn. Okay, if I take the top n minus 1 by n minus 1, I'll just call it Tn minus 1. Okay, so let's say phi n is this. So what we see is that, so this is the characteristic polynomial. So you just expand it on the last row. So what you see is that it is z minus an. So I can take z minus an here, in which case I will be left with what is the determinant of the top n minus 1 by n minus 1 matrix, which is phi n minus 1 of z. Okay, so if I take z minus an here, I'm left with this n minus 1 by n minus 1 matrix, which is phi n minus 1 of z, minus, or I can take this bn minus 1, in which case I'm supposed to take this also, and this leaves me with the top n minus 2 by n minus matrix, something like bn minus 1 square phi. So this is a recursion that is satisfied by the characteristic polynomial. So by the way, this was the definition. This is the definition, and then it satisfies this 3-term recurrence. Okay, and that is the connection with orthogonal polynomials. Orthogonal polynomials basically are things that satisfy 3-term recurrence, roughly speaking. So these fiends, so what do I want to tell here? Okay, let me, instead of, so there are a couple of things I wanted to tell. So let me maybe give a preview of that and then go into this, because I'll surely not complete it here. So one of them, so there are two, okay, there are 3 things that I wanted to say. One of them, let me say here. Yeah, maybe in the remaining time, I will only say what I want to say rather than say anything. So one of the things that I want to say here is a magical thing about eigenvalues. Okay, so suppose you fix a number x. Okay, so one of the facts that I want to get to about general Jacobi matrices is this. Suppose x is a real number, and I want to count number of eigenvalues of t above x. How many eigenvalues are there above x? You see, that is sort of relevant to my problem of studying the random matrix eigenvalues, right? If I'm going to use this, what I want to study is how many eigenvalues are above this, how many, etc. There will be randomness, but in general, if I take a symmetric matrix and ask you, I give you a number and ask you how many eigenvalues are above x, it's a complicated problem. You have to find the eigenvalues and you have to count them. It's extremely complicated. But here there is something that looks almost magical. Okay, what is this magic? So you form this sequence. So you have this x and you have these polynomials, right? So you calculate this characteristic polynomials. Phi naught of x. So that is actually 1. Phi naught of x is 1. And then you calculate the first one at this point that I have given. Okay, this x is same as this x up to phi n of x. So you calculate all these numbers, which you can do very easily using these recursions. For example, if you have the matrix, you can easily start recursing from 1, and phi 1, phi 2, etc. can be computed from this recursion. It's very easy. If I give you what the value of z is, you can, and you know ans and bns, you can calculate this very easily, this sequence. Then you calculate the number of sign changes here. The number of sign changes of this sequence. How many times does it change from positive to negative? It starts with positive. Maybe first few are positive, it becomes negative, again positive, etc. So you count how many times it changes sign. That is exactly the answer to this question. Okay, the number of eigenvalues of Tn above x is exactly the number of times this changes sign. And that is actually a magical formula which makes this actually useful. So this is called the shooting description of eigenvalues. Why shooting description? What it means is like this. So you are starting your vector. So let's say all in discrete time. I mean 0, 1, etc. like that. But let's say you are starting at 1 here, and this x is the something like a force with which you shoot. Okay. So this recursion tells you how it develops. If it is here and here, then how it is going to shoot. So you shoot with this force, which we call x. So it goes to somewhere, it goes to somewhere, then it goes to somewhere, it goes to somewhere. The point is, if x is above the largest eigenvalue, then I say that this will never say change sign because there are no eigenvalues above x. This will never hit the x-axis. So it will stay above. In some sense, it has this escape velocity. It never comes back to the origin. So what is lambda n? Lambda n is the first time when this thing actually just comes back to 0 in some sense. And after that, if you increase x, it will sort of go down. And then if you go below lambda n minus 1, it goes down and starts coming up. And if you increase lambda further, it makes further oscillations, like you see in Sturm Liouville. In fact, these are discrete Sturm Liouville operators. That's what these are. So this is the shooting description of eigenvalues. One of the things I would like to say. The other two things, I thought I would just squeeze this in, although not directly related to what I did. I mean, it's related. Are two theorems, one of Zigo about zeros of orthogonal polynomials. So if you take the sequence of orthogonal polynomials of a measure, what do the distribution of zeros look like? So there's an old theorem of Zigo about that. And there's a final theorem of Kao about the separation of roots. What this is, so if you look at zeros of phi n, it turns out zeros of phi n are interlaced with the zeros of phi n minus 1. So what Kao studied was how are these interlaced zeros spaced between here? Are these circles in the midway between the two crosses, or is it kind of closer to one of the ends? Okay, so that is a theorem of Kao about separation of zeros. I thought that these are very easy to do it from the method of moments actually. So maybe I will start next lecture by talking about these and then go on to the shooting description and the n to the minus 2/3 behavior. Okay, so I will stop here. And if there are any questions, I'll be happy to take.
Oh, okay. Thank you very much. Are there any questions? I have one concerning the part where you consider this tridiagonal representation for general V. And for gamma case, we have zero main diagonal, right? And so yeah, this first one. So can you?
Not the
Sorry.
Yeah. So
Thanks.
this is actually okay. Hold on. This is not actually. This may not contain that as the case.
Yeah. So my question was. Sorry, the connection is bad. So my question is, can you anticipate for which class of V it will be the same, zero diagonal?
No, it is not. Actually, this will not have zeros on the diagonals. I think this will actually
but maybe for some specific cases, I mean, like gamma, for gamma distribution, the first one.
Well, no, in that case, actually, you see, the thing is, this is not the matrix which has eigenvalues lambda is. It has eigenvalues. So if it has to have
it is not.
So if you take anything equally, if you take both positives and negatives, then the tridiagonal matrix will necessarily be equivalent to having zeros on the diagonal.
Yeah, okay, understood. Yeah, thanks.
So one thing nobody asked, and I also forgot to mention, this Jn I got is not symmetric. It can be made symmetric. Okay, so I mean, so yeah. Okay. Anyway, that's now I noticed that I didn't say anything about that.
And this last shooting description, I didn't catch. It is due to Sigo or who first found?
This one, the shooting description, or the
yes, this one for.
Oh no, I actually don't know. This is actually this is more or less Sturm Liouville. I mean, these are discrete Sturm Liouville. I don't know who considered matrices first. I think everything. Okay, I don't know if they were maybe not the first ones to do it, but best probably reference for these things is this Krein and Nudelman. This may be a famous book in Russia. I don't know, but not Krein and Nudelman. This other Gantmacher and Krein. Gantmacher and Krein have studied oscillatory matrices a lot. They are even a further generalization of these Jacobi matrices, showing some of the same properties. But I don't know who did it first, but that is the place I would look. That's an excellent reference for all this, actually.
Okay. Are there more questions? If it is not the case, so thank you very much, Manju, and we will continue in 20 minutes.